We were speaking of degree. So we have, for any given vertex and for any graph, so if I have a graph of order n, what's little delta of G? The minimum degree. And then capital delta, maximum degree. Great. Minimum degree, maximum degree. What does that tell you about the degree of every complete graph is the same, but they're all a specific number. All have the same degree. In a regular graph, that degree is 1. So the degree being n minus 1. Connected to all the choices. But it's not required to be n. So let's suppose the degree v equals r for all vertices in the next set of my graph. R real. A regular graph is one where every vertex is the same. In this case, so we're going to call it R. Also referred to as regular degree R. The order of my graph, I know some things about how we can make order. 8 graphs with different regular behavior. Notice you can have a graph that is 0 vertices. A graph that's 1. Wait a minute. 0, 1, 2. Bottom row, I only have 4. Can't I do one regular graph of order 5? Exactly. If I have a 1 regular graph, it means that every vertex is 1. There are 5 vertices. 3 should be 5. If I do a 3 of order 5, my total is 50. For the handshake result, I have to have an n for an odd number for an even number. So if I have two numbers, R and N, including smaller than or equal to N minus 1, bigger than or equal to 0, exists an R regular order N if at least one of R is even. And when I prove are odd, I can't make that contradiction. Get the words out. How would I go away? I'm starting with two, at least, right? Then I want to say regular. This is actually a built-in inductive proof. Suppose R and N are numbers R equal to N minus 1. And at least one of R and N is even. I'm going to assume that I N number of vertices. So we're going to say that the are one of N. I want a that is R regular on those vertices. As a matter of fact, we're even going to name it. We're going to call it N. Let's start with R. Let's suppose I don't care what n is. N could be odd. But I'm going to start with this r is even. So that means I need to connect each vertex r thing, right? Something. Hey, wait a minute. That means that less than or equal to n minus 1 over 2. What I want to do, I want to take vertices in a circle. There we go. Clockwise. I want you to take your vertex and connect it to vertices. And I'm going to do that addition mod n. So if let's say that r is 4 and k is 2, r is 4, then v1 is connected to v2 and v3. v2 gets connected to v3 and v4. v4 gets connected to v5 and 6. v2 gets connected to vn. vn gets connected to v1. N gets connected to v1 and v2. I wrap around. What's the degree of vi? Let's start with v1. What's v? Y'all are looking at me like I'm a space alien. Hang on a second. Concrete number. I said earlier, let's do R. Vertices you want. I'm going to pick medium size. How about 10? There are my vertices. What's vertex 1 get? 2 get connected to? Going. Two forward, right? So we did do. Wait a second. Look at vertex. How many things does it connect? Five, six. What's about to happen? Gonna wrap around mod n. 9 connects 10. 1. 10 connects to 1 and 2. Every vertex to the 2 and the 2 behind. Vertex connects to the K in and the K. For any I. If it's true for any of them, it's true by connecting the K behind. Just 4 and 10. Textbook. If it's deductive proof, you need to build something that was case 1. Say again. I started with not R and but N has to be even and R odd. One of them R being even, but if I start R, I have N being even. So case R is odd, N has to be even then. Because here, at least one R. So I can do one for N. So now let's start. n is 2 something, r is the same as 2k plus 1, and that means I'll let n do something else. Back to an example. If n must be even, but this must be odd. So I can't use 4. Would use 5. Believe it or not, start with the same connect each one to the 2 in front. Yes? Even comes into then is that's twice L. That means there are 5, aren't there? Pair these up. I need to split them into any 5. The this. Right? I said take the vertex and add 1 and add 2. Take the 1 and add 2, now and add 5. What do you get? You exactly 5 more edges, don't you? And those vertex exactly once. How would I generalize? Is the other one starts with plus 1, 2 up to k. Here's the special. We also can EI degree of VI, K in front, K behind, across, the degree is 2K plus 1. This is a regular R regular. There's our, there's, hey, look, their picture is much prettier. The ones that go across, all, they drew it much nicer than I did. What if I 11 vertices or 11 vertices or something like that? Well, as long as one of them is even, I'm okay. So if it is odd, R must be even. Right? So and 11. It is, it's got to be an even number, yes? That's going to be easier. Connect to the one and the one across. So this one's odd. If R is even, behind. R equals 2. Four, 5, 6, 7, 8, 11. I'm done. That's a cycle. I connect to the all I had to do, right? It's only when R was across. I wanted to do 4. When I go from 1 to 2, I go from 1 to 3 to 5, 4 to 6, 5 to 7, 8, 7 to 9, 9 to 11, 10 to 1. Everything's degree. Couldn't you? Front and the 5 behind, the only thing you can do is the one directly across. Ferrari graph. Ferrari, who, by the way, wrote a book I first ever called graph enumeration, one of the pioneers of the graph theory world. Now, please note, this is an initial, this is a constructor. You want to with guaranteed how to build it. But that's not the only possible way. If I ask you what would you draw? So you picked 5. You would already be done with this problem. I can't strictly to say that again. It's still equals 3. What do you draw? Exactly. Cycle 2 across, and that gives me a third. There's another graph on 10 sheets. Cycle on the outside, 1, 5. Side, right? And then you could connect the inside to the outside. I'm going to do that, the inside to the outside. Instead of drawing the side, circular, it's different. Same as the hierarchy. A degree of degree 3. If you want to blow your mind entry, you'll see a gazillion. There are 3 regular graphs. A cube is 3 regular. That's a cube, right? Looking down on it, bottom square, and all that. It's 3 regular. Any cycle, 2 of them in corners, you've got a degree of 3. Okay, this is Q3. Is 3 regular. K4 on 4 vertices because it has degree n minus 1. come up a lot of places to be useful, adult, helping us. So we look at the subgraph. Things. Question. It turns out that no matter what it is, be expected to be part of a regular graph. Terminology, understand? What is delta again? Maximum degree. This is for any bigger than the maximum degree. R an R graph containing G as an induced, so wait a minute, induced subgraph mean. Graph was induced by something. In from so I take away some, I leave some vertices, and I take the edges. So vertices and the graph an example. Example that looks like a pentagon. Only instead of having inside. First question. What is the maximum? What's the minimum degree? That means it's going to take me 2 iterations to get everything from 2 to 4. So the first thing I'm going to do is I'm going to make a copy of this whole graph. So here's my original graph, and here's my copy. So I've added a whole nother set of 5 edges, right? And now what I'm going to do is I'm going to connect all the things that are not degree 4 in the left picture to things that are not degree 4 in the right picture. I'm going to add more edges. So what edges do I add? I've got a degree 2 vertex over there. I'm going to connect it to a degree 2 vertex over here. I've got a degree 3 vertex over there. I'm going to connect it to a degree 3 vertex over here. I can connect to the corresponding vertices. I can connect to the mirror images. So I'm going to connect like this. This is graph 1. What is the minimum degree in this graph? As a matter of fact, I connected a new edge to everything that wasn't degree 4, right? So all of the other vertex degrees went up by 1. So I no longer have any 2s, and all of my 3s became 4s. That means that my 2s became 3s. What's the next iteration of this? Well, I just do it again. Make another copy of this, and I connect anything that's not degree 4 to something that isn't degree 4. I'm going to turn this one upside down because it'll be easier to draw my connections. What vertices down there are not degree 4? What are my degree 3 vertices? Here. 1, 2, 3, 4. These 4 in a row right here, they're degree 3, aren't they? That means these 4 down here, if I connect those, this is 4 regular, isn't it? Every single vertex is degree 4. Pick one of those 4 blobs. Take away any vertex that isn't connected to that one corner. So let's say I look at just this one. If I only have those 5 vertices, and I only look at the edges that are on those 5, isn't that my original graph? This corner looks exactly like G, doesn't it? So G is an induced subgraph by picking one set of those 5 vertices. By the way, if you start with a large graph, this is going to get effing huge really quickly, isn't it? So in the 1960s, a mathematician by the name of Paul Erdős asked, what's the smallest possible graph that would still do this? And they wrote a paper, and they found a way to do this. And I looked it up. And I want you to understand that this paper is very short. It's not even 2 full pages. I have now been looking at this paper intermittently for 2 years. It's still a brick wall to me. It's dense as hell. There is a way to guarantee the smallest possible regular graph. I don't know how to do it. There's an example in the textbook on page 43, 44, nope, page 41, that starts with this. What's the minimum degree? What's the maximum degree? It's asking me, though, for a 5 regular graph, right? So I need to add at least one other vertex to each of these. That would give me K5, because these are all connected to each other, aren't they? These 4 here in the middle. So if I added one more and connected it to everything, that would be K5. But then these would still be degree 2, wouldn't it? And if I connect that up, well, that would give me 7 vertices and 5. I can't do that. That won't be regular ever. So if I keep adding vertices, it turns out you have to get to at least 9. Well, okay, but I can't do 5 and 9. So I have to go up one more. I have to go 5 and 10. And then I build this graph with my 4 extra vertices. But my problem is I don't know where they knew to add 4 vertices. And I'm completely and totally blind to how to do that at this point. So constructing the smallest possible regular graph, I don't care about. I can construct a regular graph for any graph. It might not be the smallest one, but it's there. It's in there, and it's exactly induced. Notice they did it sideways. I did it up and down. Same pictures. Again, which graphs are allowable, which graphs aren't? There's more on this coming. We'll see you all on Friday. Have a wonderful day.